Welcome to the 15th class meeting of EECE341, Introduction to Communication Systems. The new chapter, chapter 4, is now downloadable from our secondary homepage, not in PLMS. We are going to cover it from this week, probably not today. We are going to have an exam on Wednesday night. And many of you asked whether we have a class meeting on Wednesday. Yes, we have. Okay. The exam is open everything exam except any human interaction. You have to be able to access PLMS during the exam. You are going to upload your solutions. Homework for class meeting 15 and 16 will be assigned as ordinarily. And here goes my message again, simplification and visualization. Many of you are already get acquainted with this notion, and you are going to keep seeing even our textbook doing this when the authors explain some important concepts. So they take out some unessential part in the first simplification. For example, they are assuming phase angle difference is 0, something like that. But eventually they put it back and solve. However, some of our chapters in the textbook do not inverse that simplification. And you may see some of the problems in the exam, right? So as I already told you, some of your problems in the exam will be that kind of extension or inverse of the simplification. Okay, here goes some clarifications, because last time I made statements that a little bit confuses you. So first, let me distinguish the difference between heterodyning and homodyning. Okay? Homo means same, hetero means different. So when you mix two signals, if two signals has almost same center frequency, of course it's vaguely defined, then this multiplication is called homodyning. If their center frequencies are quite different, then we call it heterodyning. So homodyning and heterodyning does not necessarily imply we consider a transmitter or a receiver. Whenever we have an RF mixing, it could be heterodyning or homodyning. The root of these words are Greek, and originally this dyne means power, but you must understand it as frequency, okay? So same frequency, different frequency. In that way, you must understand these two words. Now, heterodyning can occur in transmitter or in a receiver. Homodyning in transmitter or receiver. It's possible as you build a system in some way. We are going to see it in detail later. So today we are going to finish up chapter 3. Some of you are already bored with this long covering of this small chapter, but I myself believe that having a solid foundation with this chapter 3 will pave you a long, solid way to so-called emerald castle in Oz. So I believe this is one of the most important chapters. So that's why I covered more than a quarter of this semester. And after that, I will also spend quite a lot of hours explaining angle modulations, and then very quickly cover the last part. As I told you, we have a separate course on information theory and coding, and we have separate course for digital communications. By the way, I told you that I'm going to teach digital communications next semester, but I'm not. Okay, so I've changed it, my mind to teach digital signal processing next semester. Our communications group haven't yet decided whether we are going to offer introduction to digital communications next semester or not, but it is likely to be offered by Professor John Yosef. So you will find it. So you may take both of the courses, Introduction to Digital Communications and Introduction to Digital Signal Processing next semester, spring 25. Anyway, here goes the review of last class meeting. So first, by using a mixer, we may upconvert the signal or downconvert the signal. Here, up conversion and down conversion of a signal occurs in the frequency domain. So it's like this is input, and this is unmodulated sinusoidal signal. Then the output may be upconverted or downconverted in the frequency domain, depending on the frequencies of these two. Of course, depending on what kind of filter actually you use. Usually, the filter following a mixer is a selection filter. Sometimes it is called channel select filter if it is the it removes unwanted signal, something like that. But anyway, so this is a selection filter. So depending on the center frequencies of these two signals, who are the input to an RF mixer, and also depending on the passband of your selection filter, this mixer with filter may be called up converter or down converter. So we don't know yet whether it converts to the higher frequency or lower frequency. Now, let's see an example of up conversion. As I told you, up conversion means that you shift the signal to a higher frequency. So the simplest up conversion is direct up conversion, so-called. So suppose you have a real valued baseband signal whose spectrum looks like this. The Fourier transform must satisfy conjugate symmetry because I assume the signal is real valued. However, when you study digital communications, and also when you remember the single sideband modulation, the message signal that serves as a complex envelope of a real valued bandpass signal is not necessarily real valued. However, for the in the beginning of this wireless voice for broadcasting or communication, the engineers in that time has the objective to transmit speech signal, which as an electrical signal is real valued baseband signal. They mostly assumed this one, but not necessary. Got it? So this is a kind of zero frequency signal. Center frequency is 0. Now what you do is that you multiply unmodulated carrier. Then what happens in the frequency domain? In the frequency domain, as you well know, this multiplication, for simplicity, let me drop the phase for a while. Then you have what? You have frequency shifted versions of the message signals. So if you visualize in the frequency domain, what do you have? You have up converted to a higher frequency. Of course, you may say that, wait a minute, it has frequency negative FC, so can it be said a down conversion? No. The reason why is that in wireless communications, especially radio communications, we are interested in real valued bandpass signal, which means that if you occupy this frequency band in the positive frequency area, you must occupy this negative area too. And you don't want to say that hey, our company purchased positive frequency band 1 gigahertz from the government and negative frequency band 1 gigahertz from government. You never say that. Got it? So it is called up conversion. And if this is the desired frequency of the signal to be transmitted, then this is just a single stage up converter that serves as the transmitter. In that case, we call this transmitter a direct up conversion transmitter. So power amplifier, and here goes the antenna. Okay. So if the transmitter has this structure, we may call it has a direct up conversion structure. Got it? So directly you up convert the message to your desired carrier frequency. Got it? Of course, as I told you, in the SSB, what do? You not only have a cosine branch, in-phase branch, you also have a quadrature phase branch. And what you do may be something like this, right? Now most of you already reviewed the material on upper sideband SSB, and you know that M of t plus J M hat of t, serving as the complex envelope of a real valued bandpass signal, gives you upper sideband SSB. So M of t cosine minus M hat of t sine. Got it? So sometimes direct up conversion transmitter has two branches. And actually, in the digital communications, we do not want to waste spectral efficiency. So we do not want to, we want to increase the spectral efficiency. So in most of the times, we have not only the in-phase branch, we also have quadrature phase branch in the transmitter. Got it? So this is a more general direct up conversion transmitter's structure. The problem is that if the carrier frequency is very high compared to current technology, probably the cost of current technology, then this cosine signal itself may not have very stable frequency or very stable phase angle. Even though this has very stable frequency and phase angle, sometimes in the IQ modulator, by the way, this is sometimes called IQ modulator or phase shift modulator, the sine signal may not have complete phase coherence with the cosine signal. Then what happens? You have self-interference between in-phase components and quadrature phase component, and you don't want that. Then what do? Usually, lower frequency signal can be more can be easily generated with higher integrity. Here, integrity means that the signal's accuracy compared to the desired your target signal. So you want to generate some 30 gigahertz cosine signal, and it has cosine 2 pi 30 gigahertz t, but some phase noise. In that case, depending on the amount of phase noise, you may say that signal integrity is not that good, something like that. Anyway, so this is a direct up conversion IQ modulator or transmitter or phase shift modulator, but people devised a method that replaces expensive direct up-conversion mixing with what? Multi-stage up-conversion mixers. And that is the idea what Reginald Fessenden, who is regarded as the inventor of the wireless voice, actually patented. So his idea was like this. So instead of having single mixer, you have two mixers with lower frequencies. Now, let's see. Suppose you have two stages of radio frequency mixers. And again, the assumption is the same, real valued baseband signal, M of t. Now, what happens? So far, at this point, same. The only difference is that now this F sub C needs to be replaced by FIF1, right? Intermediate frequency 1. Now, you multiply this FIF2. For example, let's assume that FIF1 plus FIF2 equals FC, and they are all positive values. Ready? Now, what would be the spectrum of the signal at that point? And you know that each mixer right shifts the incoming signal in the frequency domain and left shifts the incoming signal in the frequency domain by the amount of this carrier, this frequency. So what you have is something interesting. So this is the assumption. Here goes our desired signal, but we have another signal here. What it is? So this one, now let's assume that FIF1 is smaller than FIF2. Got it? Am I right? Yeah, I believe so. Yeah. Then what happens? This becomes 2FIF1. And here, this becomes FIF2, I believe. Got it? And also, we have what? Here. Just a second. 2 times. Yeah. This is 2 times FIF1. So again, you have 2FIF1 and here negative FIF2. So we assume the frequency of the second local oscillator output is much higher. Actually, that is the way, because if you want to apply this idea, heterodyning, to upper sideband SSB, probably you will have the quadrature branch like this. And as I told you, it's not easy to have perfect synchronism between in phase and quadrature in very high frequency. So probably you want to choose the first local oscillator's frequency lower than the second local oscillator's frequency. Something like this. Got it? So this assumption of intermediate frequency 1 less than intermediate frequency 2 may be okay. Okay. However, it's not always. Okay. You will see some examples in the exam. Okay. Anyway, then what do you want to do? If your desire was to have this output eventually, what do you need here? You need a bandpass filter. that passes the signal around F sub C. Got it? Then what happens? This signal disappears because your filter only passes these parts. Now, when you mix a real valued bandpass signal with a real valued sinusoidal signal, you have two signals, two separate signals in the right side positive frequency and two signals in the negative frequency. And people named these signal components as what? As this signal and that signal. So this band is called upper side or higher side, I believe. Higher side. High side or higher side? Higher side. And this part is called lower side. And here we use this upper side or higher side, this type of transmitter with heterodyning two-stage mixers is called what? Called upper side tuning or higher side tuning two-stage transmitter. Got it? So we use two IF frequencies, both lower than our desired carrier, and some of them becomes our desired carrier frequency. And if we use upper side or higher side, then this transmitter is called upper side tuning transmitter. Definitely, we may have lower side tuning transmitter. And you may wonder why we use that, but sometimes you need that, okay? Actually, when I asked my graduate student to implement some proof of concept system, so we, in the right side building, have an idea. This such and such mathematical logical operations may give us some very good thing. So what we do is that we little bit move to the left side of the building and collect a lot of RF components and signal generators and program that. For example, using MATLAB or LabVIEW. And then generate the signal, receive the signal and analyze, and voila, we say that, hey, our theory is proved. That's why we call such a system as proof of concept system. Currently, many researchers not only proposes new concepts and ideas, they also build some system which may not be used as commercial operation, but it proves the concept really works. In that case, it's called a POC system, a proof of concept system. But anyway, so when we built long ago a proof of concept system, we had to use at that time lower side tuning. And you will see something interesting when we use lower side tuning. We have to flip, probably you will see, flip the sign of this adder. So plus something like that for lower side tuning to generate desired signal. I'm not going to ask you that part of the question because I believe it's too much for undergraduate. But let me tell you, upper side or high side tuning is not the only choice for you. Sometimes you need lower side tuning, which may contradict your concept because I said, hey, long ago, it was difficult to generate high frequency phase synchronous sine and cosine. So in the first stage, they used usually lower frequency, and in the second stage with single cosine, right? Because in the lower frequency, you have two branches, but in the higher frequency, you have single branch, so it's better, blah, blah, blah. that was a history, okay? Now you can generate very stable high frequency signal. So actually, even when I was a graduate student 30 years ago, many RF circuit designers said this way: direct up conversion, its time has come. Okay, so they say that, hey, having very stable sine and cosine with very small phase noise, now possible. Let's use it, something like that. But mostly before 1990s, they had this multi-stage up conversion. Anyway, let me ask you a question. This first stage RF mixer, does it heterodyne or homodyne the signals? Definitely heterodyning is occurring because this is a baseband signal and this is sinusoidal signal, right? Now, second question. In the second stage of RF mixer, are you doing homodyning or heterodyning? You can't answer it because it depends on your assumption. If these two frequencies are the same, so suppose you wanted to operate at 3 gigahertz, but your equipment in the lab has maximum 1.5 and 1.5 gigahertz. In that case, you may have the same frequency. In that case, actually, this does homodyning. So be careful. Got it? Anyway, so that is the idea. And in the receiver, you can do almost the same thing. So let's focus on the receiver. So where are we? We are here. Yeah, we've done so far. Okay, in the receiver, we have to down convert the signal. So real valued passband signal to real valued possibly baseband signal to extract our message. Then what do we do? So here is a receiver. You have an antenna and possibly pre-selection filter or pre-select filter that roughly filters out. And then you have an amplifier that adds very small noise so that you can enjoy high signal to noise ratio eventually. And then you have something. And usually, here goes another filter. And here goes a mixer. And here goes a filter. Or sometimes you have one more stage. Something like this. Okay. So let's focus on the direct down conversion to baseband. So we don't have this part. Okay. So what we want is now that we receive the signal at plus minus f sub c, but simply f sub c hertz, and we want to have a signal here, a baseband message or something similar to it, possibly a fine transform of our message signal. So for simplicity, to make everything simple, let's assume that received signal is something like this. Let me see, X. No, M. And for further simplicity, we may set theta equals 0, but in reality it's not, but anyway. So we have received the signal. And in order to extract that one, we may have what here? Local oscillator that generates cosine to pi fct with perfect phase synchronism with the received signal. So let me just say leave theta here. Okay. Now, if this filter passes the desired signal, then is it homodyning or heterodyning in this assumption? It does homodyning because the signals have same center frequency, right? Now, what will happen here? Here, again, we have baseband component and double frequency component. Why? Because here we have a signal like this. Why? Because the received signal is modeled as a real valued bandpass signal, which satisfies in the frequency domain conjugate symmetry. Moreover, we don't have quadrature phase component, which means that we have conjugate symmetry with respect to FC and negative FC if we remove the other side, right? So I've drawn this way. Now here, what happens? We right shifts this entire spectrum to the by FC. So here becomes 2FC, and we left shift by FC. So we not only have baseband components and double frequency components. And this is obvious because as you can see in the time domain, what do you have? You have AC, M of t, cosine 2 pi fct plus theta squared. And what is this? This is 1/2 1 plus cosine 2 pi 2 fct plus 2 theta, something like this. Am I right? Yeah, something like this. Got it? Yeah. So in order to extract the baseband signal only, what do you need to do? You need to do low pass filtering. So here you have a low pass filter, and that filter may be called a channel select filter because you select desired channel, which is baseband in this case. Got it? By the way, why did I put a filter here? Because even though for simplicity, we assumed only desired signal is present here or even here, actually we have unwanted interfering signals. So in radio communication, you always have to remember two things. There may exist interference. Okay? There may exist some noise. So let's assume interference present. Then what happens? That is the idea all related with what? All related with this image band and image frequency problem. Before talking about that, let's see the case where we have quadrature signal component too. So suppose we not only have this one, but also we have the quadrature phase component if we have, for example, upper sideband SSB signal. Then what do we need? Do we need just the cosine? We also need sine. So usually what we do is that we have a phase shifter that generates sine 2 pi fct plus theta, and we have a branch that mixes the signal not only with cosine but also with sine. And then we have another low pass filter and some here to have not some, sorry about that. We have the branch. A second. Okay, what happens? Yeah. Something like this. Let me delete this one. It's confusing. So in general, you not only have this output. You also have that output. Some of you are taking the communications and networks lab, and probably you will use the in-phase branch and the quadrature branch in your receiver. So even though you have received a single real-valued bandpass signal, you have two real-valued baseband signals here and there. But for the analog communication where message is real-valued baseband signal, in that case, usually you don't have this branch. However, SSB, optimal receiver must have two branches. And this structure is called direct down conversion receiver or down conversion structure. And it does what? It does homodining, right? Let me go back to, by the way, sometimes this is called IQ demodulator. In-phase quadrature components you handle. So the upper branch handles in-phase components, lower branch handles quadrature phase component. So this is called IQ demodulator. Now let's go back to the image frequency, image band problem. Not here. So here, sometimes we need a filter or not because this pre-select filter may not have very sharp cutoff. So this filter preceding the mixer may have a better frequency response even in direct down conversion receiver. But this filter really is required in the multi-stage receiver. So again, let's assume that this desired signal has very high frequency compared to your technology's cost or implementation easiness or something. Then what do? Probably what you do is that you amplify the signal, down convert to an intermediate frequency, and then down convert again. So you have something like this. So let's compare these two structures. And you will see that if you just view the block diagrams only, the difference is that you have extra filter and a mixer and oscillator. See that? You have LNA, filter, mixer, filter, two mixers, and two low-pass filters. LNA, filter, two mixers, two LNA. So this part is kind of inserted, right? Of course, the frequencies are different from this homodyne receiver. Now, let's assume for simplicity that FIF2 is greater than FIF1 and 1 is greater than 2. 1 equals, the summation is same as this. So from this assumption, you may say that, okay, probably this professor is doing upper side tuning in the receiver, and you are right. So let's see in the frequency domain. So here you have a desired signal at Fc and negative Fc. And this cosine signal right shifts and left shifts this one by FIF1. And FIF1 is very high. So here, what do you have? This is very, very important. Let me a little bit exaggerate there. So now our assumption is that these two local oscillator frequencies are all positive, and their sum is Fc. So in the first stage output, mixer output, what do you have? You right shift and left shift this one by FIF1, which is less than Fc. So it does not cross over, right? So let's say that this is around here. Got it? Okay. Now you left shift this one by FIF1. So it goes down here, and this goes to the left. Something like this, right? And what is this frequency now? Fc minus FIF1, right? This is very important. Now, and it actually is obvious, right? Because what we are going to use is that FIF2 equals Fc minus FIF, so that we do the same thing we did in the direct down conversion receiver by replacing Fc by Fc minus FIF1. Got it? So two-stage down conversion receiver can replace a single stage or direct down conversion receiver with more RF components. As I told you, one of the lessons the human being obtained from great inventions is that if you have some very scarce resource, which may correspond to expensive components, then try to find a way to replace it with abundant resource, low-cost resource, sometimes multiple of them. Got it? So it seems everything's good. So you may hear this filter may filter out these signals. And the frequency is Fc plus FIF1. And here, negative Fc minus FIF1, right? Because it is left and right shifted by FIF1. So you may have band pass filter here. Got it? So you only leave these desired signal. And then you eventually down convert. And you are done. So far, so good with possibly with this quadrature phase component that requires this second branch. The problem is that unlike this direct up conversion receiver, we have a problem, so-called image band problem or image frequency problem. Let's see why. Okay, so let's think about what would pass this bandpass filter tuned to FIF2. So the pass band is around FIF2. And you may say that this signal only, but actually it is not. That's the problem. So consider some signal components here with frequency F0, which means that it's a real valued bandpass signal, so that there is a component at negative F0. And after mixing, what happens? F0 plus minus FIF1 appears, and negative F0 plus minus FIF1 also appears here. And if two of these four may pass the bandpass filter, then this approximate equality must hold, right? And now let's see. Now, what about this one first? This is actually the desired case. So if F0 equals FC, what does that mean? Our desired signal frequency component passes through this one. But what about this one? This one says that some frequency component at F0 approximately equals FIF2 minus AFIF1 may pass. Under this assumption, this value may be negative, but it doesn't matter because on the other side, we have the same thing. So let me see, negative. Is it? Just a second. It's very confusing, right? Let me see which one. Yeah, I hope so. Yeah, something like this. Got it? So actually, this becomes positive in under this assumption, and that becomes negative, but it doesn't matter anyway. So FIF1 minus FIF2 frequency components may also pass this bandpass filter. And this frequency, F0, is called image frequency. If we consider some band, then this band is called the image band. So not only the desired band signal, but also an image band signal may pass through this bandpass filter. That's why we have this filter. And we are going to filter out the image band signal. So we calculate image band frequency and filter out that. And this is called image reject filter. Got it? So in the two-stage down conversion receiver, image band problem may occur. In order to solve that problem, we put an image reject filter. Got it? So we have covered all these things. By the way, we assumed upper side tuning or higher side tuning in the receiver, but you may also do the same thing like in the transmitter. you can design lower side tuning receiver with some filters. I'm not going to ask you that. However, last time I talked about some possible problem in the transmitter. For example, in your transmitter, you design the system carefully, but sometimes there may exist some in the two-stage, some interference goes in here between two mixers. In that case, your transmitter may transmit some strange signal, and you may be penalized a lot actually due to your ignorance. So be careful. And you may say that, hey, okay, the what professor just told us does not appear in the textbook. It may be very small or non-important thing, but this may save you in one day. Nobody knows. Okay, so read your textbook and also try to find the image or image band or image frequency in each problem. Now, let's move to the super heterodyne idea. What is a super heterodyne receiver? Super heterodyne receiver is to be used when your target signal may have non-single, more plural frequencies. So sometimes you want to tune to the KBS station, sometimes SBS, sometimes NBC, CBS, something like that. So this is our AM radio broadcasting frequency band. In Korean, 535-1605. I still remember I was taught about this frequency band when I was a middle school student. I memorized that and still remember. And there are many stations using different carrier frequencies. Suppose there are 3 signals. The contents are different. Centered at F1, F2, F3. Of course, you have the same thing here in the negative frequency. Now, you want to build a receiver. Please select LNA, some bandpass filter, image reject, first stage mixer, channel select, or again, one more stage, cosine, and actually negative sign, low pass filter. It doesn't matter here, something like this. Okay, so this is a 2-stage IQ demodulator. And now let's consider the case where you sometimes want to tune to F1, sometimes to F2, sometimes F3. What do you want to change? What do you want to change? Suppose you have fixed FIF2 or fixed FIF1. What will happen? So first, let's fix this one first. Okay. Usually, when a frequency is higher, then it's difficult to carefully change the carrier frequency too. But anyway, suppose this is variable. Then what happens? And these are fixed. So these are fixed means that here, our desired signal must be present at FIF2, right? After this mixing. Then what do you want? You need to change this one, right? And you have a fixed filter so that you can just fix this second stage part. And this channel selection filter may have very good frequency response. Or you may fix this one, but change the channel selection filter depending on your FIF1, and also change this one. Which one looks easier? And interestingly, the early radio communication engineers have found that the first one is easy. So fix the filter, channel selection filter, with very high selectivity. In low frequency, it's easier to design such a filter. So fix the frequency, passband frequency of channel selection filter, fix the IF2, but change FIF1 a little bit anyway, okay, by tuning. That is the idea. So by doing this, they could produce very inexpensive but high performance radio receivers. So as you now see, a mathematical formula may provide you a lot of different combinations of design, right? You may change all of them, right? You may change some of them. Now, here goes your creativity. And you discuss a lot with those left side building electrical engineers and decide which one is better. Probably for higher performance, for lower cost. Got it? So here goes an example. And you read it, okay? The idea of super heterodyne is to fix this second stage filters and mixers. Okay, where are we now? So cover this one, that one, and this one. Yeah. Oh, by the way, here goes one important transmitter structure that does not appear in the textbook because it's quite new. So let me draw here. So what is the most important formula equation in this introductory radio communications course? A real bandpass or passband signal, x of t, can be rewritten as what? A complex baseband signal multiplied by a complex exponential sinusoidal signal, right? And if we define this complex signal as a real part and J imaginary part, or amplitude part, no, not amplitude, let's say magnitude. No, amplitude is okay. Okay, so amplitude and phase. Okay, now you have two mathematically same but different looking equations. And if you look at these two carefully, so far, the direct upconversion transmitter or multi-stage upconversion transmitter tries to implement this one, right? Of course, in AM, you don't have that one. In single sideband signal, you have both of them, right? M of t and M head of t. But what about this one? motivated by polar coordinate representation of a complex number. That is the idea of envelope tracking technique. So what do they do is like this. So you have some signal you want to generate. You do some computation to extract amplitude and phase separately. So you build some circuit. Suppose this is easy. Of course, it shouldn't be easy long ago, right? Now, what you do is that you have here a voltage controlled oscillator. That generates something interesting. So motivated by this alternative form of a real valued bandpass signal, people started to think about a transmitter structure like this. It seems my font size becomes bigger and bigger. Okay. Good. Got it? Do you see the idea? So what you do is that you have a circuit that changes its phase, or you may say that the frequency or phase angle, depending on your input. And this appears here in the phase. And now the output here is what? It's just fixed amplitude time varying phase signal. Now you have an amplifier, and if this amplifier has a fixed gain, then this signal will be boosted. However, here, if you may build a variable gain amplifier whose gain is proportional to the power of this one. So actually, you may have to square it, but anyway. And suppose this variable gain amplifier can do this mathematical operation. Then you have generated some signal like this or proportional to that, right? So instead of using IQ modulator, you may use envelope tracking modulator or transmitter. The reason why it is called envelope tracking is that this may be understood as the envelope of the signal to be transmitted. Of course, it is not exactly envelope, but you may say that. Got it? So the reason why I teach this is that our old textbooks do not talk about this one. However, this course, this communication course may be the last course you have taken in communications area. So that's why I talk about this. This is very important. And some of your cell phones does have this transmitter structure. Got it? Now, we are going to move the last part of chapter 3. But before moving to that, let me talk about this also important transceiver terminology. You will see sometimes digital baseband transmitter or receiver, digital IF transmitter and receiver, digital RF transmitter and receiver. What are they? And some of you already have some idea. Okay, it seems that the professor just told us that everything's analog, but we may replace some parts with digital. You are right. What we do is like this. Suppose we have some signal to be transmitted in passband. So we have a complex baseband signal, which means that we have two real valued baseband signals. So we may have in phase signal. Okay, not the real value, real part and imaginary part. And you may multiply cosine and negative sign and add and amplify and transmit. And if this part is digital, then this part is called digital baseband modem. Okay, so this is done in digital domain, and these are all analog RF circuits. And then this is called digital baseband because these are baseband signals. Got it? The output of the digital part is baseband. That's why it is called digital baseband transmitter. What about digital IF? And this is actually related with heterodyning. So what we do is that we have a single output. Now this output is real part of this one. See that? This is not FC, some FIF, possibly lower than your carrier frequency, desired carrier FC. Okay? For example, FC equals 2.4 gigahertz, but your FIF is just 70 megahertz, something like this. Actually, this is the exact number I used with my graduate student to build our proof of concept system. And here goes cosine 2 pi fc minus a FIFT plus phi. And probably we have a bandpass filter to filter out lower side part, right? And then we have this transmit. Got it? This is called what structure? Digital IF structure, digital IF transmit. So you generate an IF, analog IF signal using your digital part. Of course, this digital part has what? D2A converter inside it. So you have a D2A converter and D2A converter and D2A converter. What would be the difference between these D2A converters and digital baseband, digital IF? Definitely, this signal has higher maximum frequency content, which means that if you remember Nyquist theorem, sampling theorem, this D2A converter must have very higher, fast conversion rate compared to these D2A converters in digital baseband modems. So you may say that, okay, probably this precedes in time. So this was the structure, and probably they moved to this one. You are right. Got it? So in the early stage of digitalization of transceiver, they had digital baseband modems. And then after they had very high conversion rate D2A converters, they moved to digital IF. And what about digital RF? Digital RF is amazing. They directly generate the desired signal with carrier frequency FC. So you save, of course, it's exaggerated. It seems that there is only power amp here, but it's not. But anyway, you can save a lot of RF circuitry. Of course, if you have very high fast D2A converter. So some of your friends or some of you will decide to live in this left side building forever. And your topic may be high-speed D2A converter. We may someday generate 60 gigahertz signal directly with very low cost, with very small chip. It may be possible. Okay? So you can do the same thing in the receiver. And each one may call digital baseband receiver, digital IF receiver, digital RF receiver, something like that. Okay? So these are the terminologies I want to emphasize. So have we done what? Okay. Now, pulse modulation. And it seems we are almost running out of the time, so I will be very quick. So this part is about the analysis of interference in this linear modulation. So suppose you have interference, unwanted, unintentional, or intentional, hostile. Anyway, interference is one of the most important issues in radio communications, as I told you. So people try to know what receiver transmitter structure is robust to interference. And to know that, they had to mathematically analyze the effect of interference at the receiver output. And what they do is like this. Here goes, we will be back when we study, when we compare linear modulation and angle modulation. But the idea is this one. We may not know what kind of interference would be present. Then we just do nothing? No. What we do is that we consider simplest interference. What would be the simplest interference in radio communication? What would be the simplest real-valued bandpass interference? Sinusoidal signal. That's why they assume some sinusoidal interference. See that? AI cosine 2 pi FIT. Here I means interference. You will see this kind of approach again and again in the analysis of interference for linear modulation and angle modulation, and even in some military radio. However, that is too much simplification. So usually we convert it to, or we little bit generalize it to wise and stationary random process or something like that. Anyway, so we will come back later. And here goes analog pulse modulations. And this part, unfortunately, I do not have enough time to cover. But anyway, I will try my best. So suppose your analog signal, speech signal, is simplified as this sinusoidal signal. Then you may convert it to semi-digital signal. And I haven't yet defined what is digital, but this may be represented by this pulse amplitude modulated signal, pulse width modulated signal, or pulse position modulated signal. So in this section, the authors want to expose you some technologies people have been using in converting an analog signal, especially speech or something, acoustic signal, to digital signal, and then use digital circuitry to transmit. And the name says amplitude, width, and position. And you can easily see that here you have some signal with duration t, and here only the amplitude varies depending on the amplitude of the signal. And here in pulse width modulation, interestingly, if the value is higher, then width is larger. And here, depending on the value of the signal, the position of this short pulse changes within this T sub S. Got it? So in this way, you can convert an analog signal to a digital-like signal. And then they try to for example, multiplex these signals when they build public telephone network. So let me just show you one of the ideas. So this is the idea. So what is wrong? Okay, that's all for the day. It seems that OneNote does not cooperate. Something's wrong. I don't know why.